Hi, in this video we're talking about minimally viable assay, and in this series of videos we take a scientific paper and show how we can convert the scientific content of that paper into what we're calling a minimally viable assay, and showing really how we can sort of take the first steps to commercialization. So first of all, let me sort of jump into it a little bit and say, on this occasion, we take this paper, which is the voltammetric determination of active pharmaceutical ingredients using screen-printed electrodes. So there's some useful points here that active pharmaceutical ingredients, sort of says it in the name, that this is the materials that the pharmaceutical industry will have produced. These kind of molecules are often electrochemically active, and there's an important feature of this paper, which is they're using screen-printed electrodes. So it tells you that both the application is commercially interesting, and the platform upon which they've done the work is a screen-printed electrode, and therefore it offers itself up to commercialization and sort of becoming out of the lab and becoming a real product. So if we jump into this a little bit deeper, in these kind of papers we often get a voltammogram, and this one's the same. They cover four molecules in here, and they have ascorbic acid, caffeine, paracetamol, and this DX in there. So there's a voltammogram, and they've labeled it up, and we can essentially see each compound has a distinctive peak position. And also, if we analyzed the peaks a little bit more, we probably find that there was also a more distinctive shape, let's say. But the paper contains voltammogram, but what we want to really discuss is actually how to convert that voltammetry into something that's, I would call it more like information, something that can appear on a smartphone and tell somebody who's not an electrochemist, there were 20 milligrams per liter of paracetamol or something like that on the or in the sample rather. So on this video we want to go from scientific paper to really what we call minimally viable assay, and that's based on the principle of minimally viable product, which is a kind of Silicon Valley concept. So let's dive into this a bit more now and say, in this kind of work, as we've already said, here we have the voltammetry. In this particular paper they use a lot of DPV, differential pulse voltammetry, but we wouldn't mind if it was square wave voltammetry, linear sweep voltammetry, cyclic voltammetry. Voltammetric methods are quite nice because they're quite feature rich. Here we've just sort of pointed out where these particular molecules appear. They have a sort of distinctive, let's say, voltage, and probably within the context of if you were monitoring the wastewater from a pharmaceutical manufacturer, within that context, then you could probably make a positive identification that if you saw this let's say voltammetric peak or voltammetric curve at this voltage, and it was in the context of the wastewater from a pharmaceutical company, then you could say with some degree of certainty this is that particular molecule. Now as I say, the voltammetry that they're using here is DPV. Voltammetry is often this is a voltammetry of a organic molecule, and it's sort of very, let's say, distinctive. This is the voltammetry from a organometallic compound, and its voltammetry is also distinctive. Now the reason being is I want to sort of step away and say, let's not treat this as voltammetry, let's treat these as fingerprints. So what we're saying is that voltammetry that appears in these scientific papers contains qualitative information. It can tell you what the molecule is, and it can also then through the peak heights, for example, give you quantitative information, i.e. how much of that material is in that particular sample. So we like these kind of papers because the application they're facing is commercially viable. The screen-printed electrode platform means that it can lend itself towards commercialization, and voltammetry itself is feature rich. So here you can see that we can both analyze a fairly complex matrix of four compounds, and we can also quantify those compounds within this sample matrix. So going forward a bit, now at ZP we're very different. We're very sort of when we support academic work through the sale of standard products, what we're really sort of imagining is that everyone really wants to get to market. So at ZP, we have a very good low cost, something we call a hypervalue carbon electrode. This electrode is less than 50 cents per electrode. It's really high quality. We also have some graphene electrodes as well, which I think are approximately €2 per sensor. So the reason I mention this is because at ZP we have a view that actually, these products are one day going to make them way to market, and so we want to make these kind of things like screen printed electrodes intrinsically low cost. So the kind of platform that we have at ZP is we have screen printed electrodes, including carbon and graphene. We have we call it an omnisense, but really it's a sort of, it is actually a potentiostat, but it gives you a very different experience because as much as electrochemists love electrochemistry, end users in the pharmaceutical industry, for example, don't want electrochemical data and signals. They want final values. So I'm going to show you that this is, though a fully functional potentiostat, it gives a very different user experience. It's thinking about the end user as opposed to the R&D scientist. We also have something at ZP called Julie, and this is sort of critical to this whole thesis that we can get from lab R&D to minimally viable assay very quickly, because actually we have this cloud database. And these three elements all work together, and I will discuss that now. So we not imagine, but we know that these screen printed electrodes will slot into the front of these meters. The sample will go on there. The sample will contain the sample matrix that was from the original scientific paper. And then the Omnisense meter, or this meter, will actually work with an app. And this is something that we have at ZP. Now this app tells the meter what to do, and it tells it by Bluetooth. And it's good because actually we have that. This is the great thing about these scientific papers, that we actually have the method file from the original scientific paper. So we can essentially extract that method, put it into the app. The app tells the meter what to do. And now importantly, the meter gives the data back to the app. And the app has an upload button. So now we're going to move all the complex, let's say, data science off the app up to the cloud. And I'll show you how that works. So we have something called Julie. Julie is a proprietary database. It can receive data from ZP potentiostats. It can receive data from CH instrument potentiostats, from Autolab instruments potentiostats. So Julie is probably the only proprietary database around that can actually receive electrochemical data. So it's not hard for us to move raw electrochemical signals, including differential pulse voltammetry, up to the cloud. So we can move that kind of data up to our Julie cloud. If you Google Zimmer Peacock and Julie with a D, you'll soon find this database. And now in this database, what we can do is we can actually do essentially peak recognition, and say, can we see these 4 compounds? And we can also, this is linked to the calibration, which is the second step, but I'll come back to this. So the first step is actually almost like feature or compound identification. Within the context of, we are analyzing, for example, wastewater from a pharmaceutical company would be a classic. Within that context, are we able to identify compounds in that wastewater? And if so, we can then identify them and say, use a lookup table and say this voltage therefore means that we think this is, paracetamol, or this is caffeine, for example. So we can identify the compounds. We can do things like baseline adjustment and then sort of peak measurements. The next part is first of all identification, which I call qualification, and then it's quantification. Actually, the database will allow us to have, for example, uploaded a calibration graph, and we can then look our things like our peak height, and from there actually calculate what our concentration is. So let me just kind of summarize a little bit so far. So we like these strong papers. They're an example in this one. They have a application which is pharmaceutical, which is interesting. They use screen printed electrode, and all we're demonstrating here is actually there's a stack of technologies at ZP, which means if you come on to our screen printed electrodes, we actually have the whole roadmap determined to run the sample on the screen printed electrode, upload the data, analyze the data in Julie, quantify it, or qualify it rather, quantify it, and now the last step, which is having gone through this quantification of calibration, we can then deliver in the cloud, for example, the concentration 20 milligrams per liter. And so if I was to summarize this, where the scientific literature finishes, for example, voltammetry, actually, if you're on the ZP platform, you're really on your way to actually going from scientific data to critically information, which then somebody in the pharmaceutical industry can adopt that assay much easier. And actually, we would not display the whole voltammetry and baseline adjustment and calibration. For the pharmaceutical scientist, we would actually just display the 20 milligrams per liter, because that's really what they want to know. So if you have any questions regarding the ZP platform and the way it can actually move a assay from interesting scientific paper to minimally viable assay, then please don't hesitate to contact us at ZP. Okay, thanks very much.